How many of y'all been to Kohl's? Does anybody shop at Kohl's anymore? Okay, cool. All right, cool. So Kohl's used to do this whole like $10 cash every time you spent like $50. I think they still do it. For every $50 spent in the store, customer receives $10 in Kohl's cash. Credit customers can use the purchased items in their next store visit. Customers only receive the cash for every $50 spent. My mom used to like buy us school supplies or school clothes and then rack up on it. And then Christmas, she would use Kohl's cash. That's what she would do. If a customer spends $240 at a Kohl's on a shopping trip, how much Kohl's cash will they receive? Go ahead and take a moment, type that in. How much Kohl's cash will they receive? All right, so we got a couple people saying 40, okay? And we need to explain how we know. How do we know? How do we know? What was the information that they told us? They said we get $10 Kohl's cash every time we spend 50 bucks, right? So if we spent $100, we would get $20, right? If we spent 150, we would get 30. If we spent 200, we would get 40. If we spent 250, we would get 50. And y'all are saying 40. Right? Good. So y'all kind of understand how to do it. So when a customer spends $240 at Kohl's, they receive $40 in cash. This is because 50 plus 50 plus 50 plus 50 plus 40. So they would receive 4 $10 rewards. All right. So it's a busy day, Saturday at Kohl's. Each one of the points here represents a customer at Kohl's, each who spent a different amount of money. Slide the points up and down so that each customer has the correct amount of Kohl's cash provided. Okay, so for instance, I don't know if I can, there we go. Okay, so you can move these points. I don't know if it's gonna allow me to do it. Okay, cool. All right, so take a moment. You're moving the point to represent how much money they've spent versus how much Kohl's cash they're gonna have. So if they spend, this looks like roughly 30 bucks. Are they even gonna get any Kohl's cash? No, so they'll have 0. Does that make sense? You would drag this point down to the bottom. Okay, so take a moment. You're working on that. All right, so let's see what you got. Oh, now I can actually see it. Okay, so when we move this, they spend about 30. That's going to be $0 Kohl's cash. If they spend, it looks like, I can't tell what number that is, but if they spend more, then we would at least get $10 Kohl's cash here. What about 200? More than 200. This looks like 250. So how much Kohl's cash am I going to get? 50. Okay, if I spend between 250 and 300, that's going to be roughly here. If I spend about, this is like 425-ish. How much is 425 going to get? Like 80, right? 60, 70, 80. Okay, this one's going to be right here. And then this one is about 550. So that's going to be 100. Okay, we kind of see that there's these little like steps, right? All right, so making a sketch of what you believe this graph is going to look like. Well, from $0 to $50, we're going to have 0 Kohl's cash. Once we hit $50, that's when we're going to get $10, right? And then once we get to 100, we'll get 20. Once we get to 150, we'll get 30. Once we get to 200, we're going to get 40. So it kind of looks like a little step, right? Okay, so this is called a type of function, and we're calling it a step function. So this is just a special type of piecewise function that are made up of only constant equations. Okay, so looking at the example of the step function to the left, to the right, the graph is a bunch of increasing segments this is what a typical step function looks like. So similar to what we just saw. Okay. I want you to go ahead and skip slide 8 because we just went over that. Go ahead and go to slide 9. And so it says, in 2015, the cost for sending a letter by the United States Postal Service is 49 cents for up to 1 ounce, plus 22 cents for each additional ounce up to 7 ounces. So type the equation for the step function on the lines below. Okay, so the information that they give us is they say that you're going to spend 49 cents up to 1 ounce. And then you're going to add on 22 cents for each additional ounce up to 7 ounces. All right, so let's talk about below 1 ounce. How much is it going to cost us? Below 1 ounce is going to cost us how much? It's going to cost us 49 cents, right? So we're going to say 0.49. And we're going to say that's from 0 up to 1 ounce. Okay, notice how I use these little swirly brackets right here. I don't actually know the real term for that one. But we use these brackets so that we can, curly brackets? Is that the like actual name for them? That's crazy. Okay, so this is gonna state our domain. Okay, notice how there's like a little red line down here at the bottom. You can't really see that. You need to pull down that thing. All right, then it says plus 22 cents for each additional ounce. So when we go from 1 to 2, we're gonna add 0.49 plus 0.22. And that's gonna be from 1 ounce to 2 ounces. On the next one, we're going to add another 22 cents. So we're going to say 49 plus 0.22 plus 0.22. And that's going to be from 2 ounces to 3 ounces. There we go. Okay. On the next one, we're going to have 0.49. So we're going to make this a little easier to like write out. We're going to say 0.22 times 3 because we want 3 times that 0.22. And that's going to be from 3 ounces to 4 ounces. Can you do up to 7 ounces? So kind of following this pattern. On the next one, we would have 0.49 plus 0.22 times 4. And the next one, we would have 0.49 plus 0.22 times 5. And that would be from 5 to 6. And then we would finish it up 0.49 plus 0.22 times 6. And that is what our step function would look like. Looks like a lovely game of Mario, right? Boing, boing, boing. Okay, so let's go ahead and look at slide 10. This is what you're going to probably see most often. They're going to give you some type of scenario, and then they're going to say, write the equation for the situation. Okay, so we got a big sale this weekend, only up to 2 hours of work, it's $50. After 2 hours of work and up to 5 hours, it's $100. And then after 5 hours of work, up to 8 hours is going to be $200. Okay, so write the equation for the situation above in the box below. All right, so we're going to go from up to 2 hours of work. How much is that going to cost us? $50, right? So our equation is going to be 50. And we're going to say from 0 hours of work up to 2 hours of work. Okay, you need to know how to do the domain restrictions. That's that little curly bracket, right? On the next one, okay, on the next one, we have $100, and that's after 2 hours of work and up to 5 hours. Okay, so we would write the equation y equals 100. And what's my domain going to be on this one? Well, it says 2 and up to 5. So 2 and up to 5. One thing I do want to note is that this says after 2 hours. So that's including 2 hours, right? Okay, so instead of it just being this little inequality symbol, what we're going to do is we're going to use the underlined inequality. And the only way that you can type that is you have to use your keyboard. All right, and the last one, we have y equals $200, and that's from 5 hours, and it said up to 8 hours. Okay, and again, we want to make sure that we use that equals on this one. And we're going to put equals as well on this one, actually. There we go. Okay. All right, so what I want you to do is on slide 11, write this step function out. Okay, take a moment, try that. I'm going to check your work in just a second. Okay, let's talk through this one. It looks like most of you have said for up to 1 hour, it would be $30. Okay, good. On the next one, for $55, we have from 1 to 2. Good. Don't forget, you have to include our little line underneath because we're going from 1 to 2. Okay. And then on the last one, 90. And remember, it's including 2 hours up to 3 hours. Okay. Good. So can you figure out what values are below? So when you do this, what's up? It should be 11, roughly. 13. Wow, way off. Way off. I failed. Okay. So what you're going to do here is you're going to look at this number. Okay. And we see -2. And we're going to look at the domain restriction. So which equation, either 1, 2, or 3, is -2's domain fit inside of? So which equation, either 1, 2, or 3, and I put the numbers up on the board, does -2's domain restriction fit inside of? Again, some blank stares. So what I'm asking for is, like, for instance, this right here says from -6 to 2. Is -2 inside of -6 to 2? Like if you put it on a number line, -2 would fall in between those two numbers, right? Yeah. So if I have, oh, I can just use this. So looking at this graph right here, from -6 to 2, and -2 is located right here. Those are in between those two numbers, right? 2 is here, -6 is here, this is -2. Yes? So we're going to use this equation. Okay, so we're going to plug in -2 into this equation. When we plug in -2, fortunately, they have our graph right here. our y value is 4. So that's going to be equal to 4. Looking at this one right here, we see 6. So we're going to look at our domains. Okay, and we have two options that have a 6, right? Remember, if we have a line underneath, that means equal to 6. So that means that we're going to use this equation. So we're going to plug 6 in to this equation. So we have -2 times 6 plus 7. Well, -2 times 6 is -12. -12 plus 7 is going to give us -5. And when we look at the graph, we can see at when x is 6, our y value is 5 right here. Can you try to fill in the next two? All right, so on this one, x is 0. So which one of these equations am I going to use? 1, 2, or 3? Well, let's think about it. 0 is in between -6 to 2, 2 to 6, or 6 to 10. I think the number 0 is in between -6 to 2, right? So when I plug that into here, I'm going to get 1/2 times 0 plus 5, and that's going to give me 5. I'm going to look on my graph really quick to check that. When x is 0, where does it meet the graph? At y equals 5. On the next one, we have x equals 7. So which one am I going to use? Well, 7 is in between 6 and 10. So when x is 7, what's our y value? Just 1. And we can check that with our graph. When x is 7, what's our y value? 1. Okay. On the next one, when x is 2, this one's a little tricky. You got to make sure that you pay attention to the equals, right? Well, since this line is here, that means that it's equal to 2. So we're going to plug 2 into this equation. And we're going to get 6. We can check that with our graph by going to when x is 2, our y value, and we want to look when it's a closed circle. If it's an open circle, that doesn't work. It has to be a closed circle. And this one's a little bit off our page, but it's up here. When x is 10, our y value is 1. Can you try f of 5? All right, so when x is 5, looking at our domain restrictions, we're going to use this guy. We're going to use the middle one. That's going to give me -2 times 5 plus 7. And so that's going to give me -10 plus 7, which is -3. Looking at our graph, we can check that. When x is 5, our y value is -3. The last one's tricky. F of 11. Okay. Is there any restriction when x is 11? Does that fit any of our domains? No, that's outside of our domain. So we're going to call this undefined. Or does not exist, or you can say no solution, depending on what test you're taking. They might have a couple different wordings. All right, so we are going to graph piecewise functions. So we kind of talked about this yesterday. So how to graph these. Separate graph based on domain. Okay, you can do that. And then make an XY table for each equation, and then you're going to graph. I can make sure the shape of the graph matches the equation. Okay, so what they're telling you to do is to make a table and then fill in that table based off of these 3 equations. Okay, what I like to do is kind of in my mind is I like to section these off. So for instance, this says x is less than or equal to -1. So right here, I know that at x equals -1, that's where this graph is going to stop. Okay, so I'm going to go ahead and graph this equation. If you don't remember how to graph these equations, remember you always start with your y-intercept of 2, or whatever your y-intercept is. Draw that. And then you're going to use your slope to write out the rest of the equation. So this has a positive slope. But remember, I want to graph it on the left-hand side because of this domain. So I'm going to go over 1, down 1, over 1, down 1, over 1, down 1. I'm just going to continue that pattern. I highly suggest you don't do this in pen because you're going to have to erase some stuff. I'm going to connect this line. If I can draw a straight line, good grief. And then I'm going to add an arrow on the end. Now they said x is less than or equal to -1. Okay, so that means that I'm going to get rid of this dot on the y-axis because they want us to stop at x equals -1. On this next section, they want it from -1 to 1. So I'm going to draw like my little boundaries from from -1. Wow, can't get that straight at all. So 1. Okay, and they would say that the y value is just going to be 1. So it's going to be a horizontal line from -1 to 1. I'm going to draw straight. Okay, so from -1 to 1, it's going to be a straight line across. Now, they are both going to be open circles. So we're going to draw an open circle at 1. And there would be an open circle here. But since there's another point right there, we're just going to leave a little ring around it. We're going to get rid of those little highlighter lines really quick. The last part is x is greater than 1 or equal to 1. So we're going to go ahead and draw our boundary. Okay. And then we're going to plug into this equation. Now, I don't know what x squared looks like. Let's say I forgot. I could use Desmos, right? So if I go into Desmos and I graph, nope. Okay, so if I go into Desmos and I graph x squared, I can use the table. And remember, I only want it from 1 to positive infinity. So I can go ahead and get rid of these. And I want numbers that are bigger than 1. So I'm going to write this little table down really quick. So I'm going to go x, y, and I'm going to say 1, 1, 2, 4, 3, 9, and then I think the rest goes off my graph. So coming back in here, I'm going to graph the points 1, 1, 2, 4, and 3, 9. Graph those. 1, 1, 2, 4, and 3, 9. And that's probably going to be off the page. That's going to be up here. I'll connect those dots. And then I'm going to get rid of my highlighter. Now remember, this is always check your dot to make sure that they need to be closed or open. Right here, it has a line underneath, so this guy's going to be closed. I'm a very visual learner. And so I used to like to do colors on these when I would draw them out, just so I could see which piece goes with what. If that's something that you like doing, I highly suggest graphing it that way. Now, I'm going to be honest, on the next one, I totally would not do this by hand. So I would definitely use Desmos graphing calculator. So I'm going to write these down really quick. And then we're going to plug this into Desmos to make our lives a little bit easier. Okay, So if I go into Desmos, and I'm going to type the equations just as they are written. Second power. Now, when I put the domain in, the domain restrictions, remember, I'm going to use a little curly brackets, and I'm going to say X. You're going to hit Shift, and then there is a bracket that looks like this. So the little box brackets. No, the actual circles. And then when you want to put in X is greater than or equal to, you're going to have to go to the keyboard, and you'll have to use this keyboard. So we're going to say X is greater than or equal to 1. And notice how it graphs the equation, but it cuts it off right here because we gave a domain restriction right here. We're going to type the other one. So X plus 3. And then again, use the little curly brackets. And we're going to say X is less than 1. Ta-da! So you can take a moment, and you could also look at the tables and then graph the points. So if you want to take a moment and draw this graph on your paper, I'll zoom in a little, maybe give you some points. Okay, so take a moment, draw this on your, again, I would probably suggest doing this in Desmos. I'm going to help you out. I'm going to graph it in Desmos. One thing to keep in mind, we're not going to be able to tell you, hey, you've got to use little curly brackets to do the domain restrictions. Okay, so you have to know that all on your own. Okay, I'm going to write this down, and then we're going to put it into Desmos. Should be like page 13. Ooh, nope. Wrong. Okay, so we're going to put this into Desmos, and then we're going to plot it. Okay, promise we're almost done. Okay, so on this one, are you going to type a 0? And then you're going to put the little curly brackets. Remember, that's going to be Shift, and then the little bar, kind of like right above the enter button. Okay, and then that's going to be from -5 to 2, -2. All right, the next one, -x squared plus 4. And then that's from -2 to 1. I don't know if that's right. I gotta go back and look at it. And then -x plus 3. And that's going to be from 2 to 5. Oh, that's right. Okay, so go ahead and take a moment, and I want you to write this down or draw this out. And then we're going to talk about open circle versus closed circle, because that's very important. So on here, you see how there's no like open circle versus closed circle. So Desmos doesn't do a really good job of like showing you that. However, when you click on like the endpoints, it either has a number or it says undefined. Okay, so that's one way to kind of see it. But what you're going to see most often on your test is closed versus open circle. So if it has a line underneath, that's going to be a closed circle. If it does not have a line underneath, that's going to be an open circle. The problem is when we have an open circle and we have a closed circle at one particular point, it's going to look kind of like this, where it's got a dot and then it's going to have a circle around it. Okay, for this one, we would have a closed circle, And then for this one, we're going to have open circle, and then we'll have a closed circle down here at the bottom. Okay, those do matter because if you have two functions that are on the same x value, and you have something like an open circle down here, but a closed circle up here, then this is what's going to be your y value. An open circle means that there is no y value at that point. Okay. All right, so what I want you to do is take a moment. How do I know when to use an open dot, a closed dot, or arrows for the endpoints of each function? I want you to write like a little thing for that because we just went over that. How do I know when to use an open dot, closed dot, or arrows at the end of each function? Take a moment. All right, so we just talked about this, but if there is a line underneath, so if it has a greater than or equal to or less than or equal to, then it's going to be a closed dot. Okay, if it has no line underneath, it's going to be an open dot. Okay, if it goes to infinity, it's going to be an arrow. So like this would be something like x is less than -5. Then there's going to be an arrow on the left-hand side. Okay, if it just kind of continues on, if there's no boundaries for that section. Okay,